combination reactions. Combination reactions are simply a reaction where you're taking two things and you combine them together into something new. So for example, if I take H2 plus O2 and it produces H2O, that's combining hydrogen and oxygen into something new. That's a combination reaction. Okay? So that's a combination reaction. Decomposition reactions are simply the opposite of that. You're taking one thing and you're decomposing it into what it was before. So, if I reverse this reaction, now it's a decomposition reaction. Combination. Decomposition. Because it's decomposing into its elements. Okay? Into what it was before. Not necessarily have to be an element, but it decomposes into what it was before. So it's essentially the reverse of a combination. Decomposition, the reverse of combination. Single replacement reactions, those happen when you have one thing and it replaces something else that has a partner. Okay? You have something that has a partner, that one thing replaces it. And it's a single replacement. Double replacement is where both partners switch. Okay, and we're going to look at those. Well, not exactly. Since these are elements, so they don't really. Okay. Okay. So here we have a combination reaction, A plus B forming AB, right? And here's some examples. Sodium and chlorine forming sodium chloride. So it's interesting that you can take these really dangerous chemicals like sodium metal, very reactive, and chlorine gas, which is deadly if you inhale it. Okay, it will kill you. You take those two things and you put them together, and now what does it form? Yeah, something you eat every day. Okay, don't eat too much of it because maybe it is deadly. Okay, but nobody's scared of some sodium chloride, right? So that's what happens with chemical reactions. Chemical reactions occur because you have something that is very reactive with something else that's reactive. You put them together, and now they're not reactive. They were reactive because they were all energized and this stressed out. I'm going to put that stressed out state, and then they come together and they calm each other down. And now you have sodium chloride. Okay. Magnesium oxide, carbon dioxide, they come together. Combination reactions produce magnesium carbonate.
The S is single or what is the S?
S is solid.
Solid. And the other is gas.
This is a gas, yeah. That's a solid metal, sodium, and this is gas, chlorine. Yeah. Those are the physical states. AQ means aqueous, and we're going to look at that in a minute as well. But yeah, that's what those mean. Okay. Decomposition reactions. Mercury oxide decomposes into mercury and oxygen. Calcium carbonate decomposes into calcium oxide and carbon dioxide. Okay? So it's decomposing into what it was before. If I reverse those reactions, they become what types of reactions? Combination reactions. Okay? So decomposition is essentially the reverse of a combination reaction. Okay, now for single replacement. So in a single replacement reaction, you take A and it replaces B. Okay? And that's a single replacement. B comes out all by itself, and now AC is the constant. So for example, we did this in the lab actually. You take copper, you put it in a solution of silver nitrate, and all of a sudden what's going on? That silver starts to precipitate, starts to come out of solution, and the copper starts to dissolve. And now the copper is an ion, copper 2+. And now you have a solution of copper nitrate instead of a solution of silver nitrate. And the silver comes out. You have essentially purified all the silver that's in there. So,
what means the partition AQ?
Aqueous means that it's dissolved in water. It's an aqueous solution, which means it's dissolved in water. That's what AC means. These things you're not going to have to worry about too much if you're taking another chemistry class. They'd be more important. Well, there'll be a little bit of importance in this when you get into things like rate and equilibrium, but other than that, also chapter 5 we're going to talk about gases. So most of the chemical reactions that we do with gases, they need to be in the gas state. So, but it's good to understand what those stand for. Solid, liquid would be just an L. Aqueous means it's dissolved in solution. So here, when I say aqueous, that means that I have silver ions and I have nitrate ions. They are not actually together, right? Because they're in water. And when you put an ionic compound in water, what happens to it? It breaks apart. You have silver ions and you have the nitrate. The positive cation and the negative anion. They break apart in water. And that's why it says it's aqueous. If I took away the water, it would come together as a solid product, then they would be together. But as an aqueous solution, they're actually pulled apart. Okay? And that is actually going to come and play into what we're going to talk about next with precipitation. Okay, but first we want to talk about single replacement, double replacement, to understand how that kind of all works. Okay, so copper is going to replace the silver. So if you knew a source of silver nitrate in the earth somewhere, you would make a lot of money because you could just go to Home Depot, buy some copper wire, throw it in your silver nitrate, and all of a sudden you have pure silver. Okay? Well, but the silver would be worth more than the copper, right? So you would be able to purify. For every copper atom, you get a silver, right? And the silver would be worth more than the copper. And there's also other metals that you can use to do that besides copper. What? You would need a source of silver nitrate. Good luck. You'd have to find a source of silver nitrate. Now, there are sources of gold in the ocean, gold ions. And that's one thing that a lot of people want to do, a lot of chemists. They want to figure out how to purify those gold ions and pull them out so that they can make a lot of money, right? So, yeah. No, they want to make money. So, yeah.
Like what makes something, like is that how it was gold was precious, like because it's rare?
Because it's rare. So yeah, once it becomes less rare, it's not as precious anymore, right? So it might not be worth as much. So right now it's worth plenty. So it's still worth a lot. Okay. Sodium, you put it in water, very violent reaction. If you drop sodium in water, it'll burn you. Oh yeah, it's nasty. No, don't try it. Okay? And it will produce sodium hydroxide and hydrogen gas as a result. So that's a single replacement. This sodium is replacing one of the hydrogens here and causing it to now be, instead of a hydrogen right here, to be a sodium OH. sodium hydroxide, and the H's that come off, they find each other and become hydrogen gas. So that's a single replacement reaction as well. Nope. Sodium's a metal. Sodium chloride is salt. So if I have chlorine and sodium together, they form a salt.
So how violent is this reaction?
Like crazy boiling water, burn you. Oh my God. Don't do that. That would be very, very dangerous.
Boil up?
Yes. And the hydrogen gas is coming out and causing the hot water to burn your skin. And
So if I have a pot of water and I don't want to make noodles put it on fire, I
Oh
can
my
throw
God.
a little piece of sodium in there and it'll boil my noodles.
I suppose that in theory that could be true, but I would not recommend that.
Okay.
Don't do it.
So
Hydrogen's not poisonous, so it's not. Well, the sodium poison my noodles.
it could, yeah.
Tar.
Okay. So, but in any case, that is a violent reaction, and you produce sodium hydroxide, hydrogen gas through it. Okay. Now, double replacement reaction. Double replacement reaction, for some reason people get all confused about this, but it's really easy. Okay? All you do is you take the first element, which is the cat ion, and you switch them. So A will go with D, and C will go with B. So I will produce AD and CB. These guys just switch places. That's it.
Is it always a cat?
Well, you can think of it however you want. You could think of it as the anion switching place. Doesn't matter, okay? But I'm just going to say it that way to keep it consistent. Just switch the cations. Switch the cations, and now you have a double replacement reaction. That means I need two ionic compounds. I need one ionic compound and another ionic compound, and they will produce a double replacement exchange reaction. Yeah. Yep. Well, that's the most, okay, I won't say only, but for the most part, that's what you're going to see. A double replacement reaction will occur with two ionic compounds. The cations will simply switch partners. Okay?
So one of the ions has to be positive and one has to be negative, or it could be both positive and, you know.
You were right the first time. One of them has to be negative, one of them has to be positive. So, for example, the example that they were just going to show, lead nitrate plus sodium chloride. Two ionic compounds. What are the products of this reaction? Good. Switch what? Switch the partners. Switch the cations. Yes. NaNO3. Okay? Now, who can tell me the correct formula for lead chloride? PbCl2. Yeah. Why? Because this lead has a what charge? 2 positive. How do I know that?
Because Cl has 2 negatives.
Because I have 2 nitrates. You see how I have 2? Bring that 2 up. It's lead 2, right? Lead 2 nitrate. And I have sodium chloride. So Pb2 plus, NO3 minus. What do you mean I have to change the charge? I have 2 NO3s. The charge of NO3 is -1. That's why I have two of them to balance the 2 positive charge on the lead. That's why I switch it up. I bring it up, it's lead 2 plus, and it's NO3 minus 1. Sodium and chlorine, 1 and 1. Okay? But those guys I can find here. Sodium plus 1, chlorine negative 1. Okay? So, here they are. They switch partners. Lead 2 plus goes over here with chlorine, and sodium comes over here with nitrate. Because the cation, okay, well that's actually a good question. Lead, if it's going to react with anything in this reaction, what would it be? It's already with nitrate, so it's not going to react with nitrate. It's already with it. So is it going to react with sodium or chlorine? The lead. Why? Because it's negatively, it's the anion, right? Can I have lead and sodium come together?
No.
It's 2 positive charges. What's going to happen?
Make the break.
They're just going to repel. They will not come together. But sodium and chlorine, lead and chlorine, they will come together. Okay? There is an attraction there that will come. And then same thing here. Sodium and nitrate. You have to have a cation and an anion. The cation is always written first. So when I write the potential products of this reaction, I say lead chloride plus sodium nitrate. Those are the potential products of this reaction. I say potential because both of them actually don't form. And we'll see why in just a minute. Okay? So here, okay.
So, NO3, the negative one.
This one.
Yes, good. So when you write it down from octave, I thought the 2 multiplies everything in the parentheses.
It does.
Okay.
So you have 2 nitrates for every 1 lead. Yeah. That's what it means. You have 2 nitrates for every 1 lead.
And then the oxygen is supposed to be 6. If the 2.
Okay, no. No, all that means is I have an NO3 plus another NO3. Now, if I was calculating the mass of lead 2 nitrate, then I would calculate 6 oxygens and 2 nitrogens because I have 2 of them. I have 2 NO3s. So I have NO3 and NO3. So it would be NO3 and NO3. That's 6 oxygens, right? And 2 nitrogens. That's why I have 6 oxygens and 2 nitrogens, because I have 2 of them. Not because the formula of it is later written as N2O6. That's not how I write it. It's still an NO3. It's just an NO3. And NO3, it's a negatively charged polyatomic ion. Okay? So I have a lead, I have an NO3, I have a sodium, and I have a chlorine. Now the amounts of those I'm not writing here, because I could say I have 2 NO3s for every 1 lead and 1 sodium and 1 chlorine. Okay? But I didn't do that because it's not important to what we're doing here. Okay? So, lead chloride plus sodium nitrate, those are the products of this reaction. It's a double replacement reaction. Alright, so we can see that's what we got here. Now you'll notice this was written as aqueous, and this was written as aqueous. What is this written as? Solid. This is still aqueous. So, what does that mean? Well, this is what it means. It means if I have a test tube and another test tube, and I put lead nitrate into one of them, okay, it will dissolve into water. So when it dissolves, I'll have lead 2 plus, NO3 minus, lead 2 plus, NO3 minuses, and they're just distributed throughout. They're dissolved, right? They're broken apart. And then in the other test tube, I have Na plus and Cl minus, Na plus, Cl minus, Na plus, okay? And they're all distributed throughout as ions. And then I take this tube, and let's get a third tube. I pour these 2 tubes into this third tube. Now what happens? Well, lead 2 plus, Na pluses, Cl minuses, NO3 minuses, they're all in here, right? They're all together. So does a reaction actually occur? That's the question. Does anything actually happen when I pour them all together, or do they just all remain dissolved? And the answer to that question is yes. Lead chloride becomes a what? A solid. So the leads will go around and they will find the chlorines and they will become a solid product. Instead of being dissolved in the water, they don't dissolve in water. Lead chloride is insoluble. So it falls out of water, it falls out as a solid product. So you have 2 clear test tubes, you pour them all together, boom, you get a solid product. So something else you guys did in the lab. In fact, with lead, I think it was lead iodide. Took lead nitrate, and some sodium iodide. It's 2 different test tubes. You poured them together, boom, it turned yellow. Remember, you guys remember that bright yellow, canary yellow, they call it. Oh, the volcano thing. Did we do a volcano? You could do a volcano. That's true. No, that's not how you decide it. We cannot on our own predict it. Okay, but there is a chart that we will learn to use to learn how to predict whether this happens or not, whether it becomes an insoluble solid product or not. Okay. Okay, so let's, already done that. There it is. So, we call these precipitation reactions. Precipitation reactions are chemical change in solution that result in one or more insoluble products. That form together, an insoluble product forms, and it comes out of solution as a solid product. To predict if precipitation reactions can occur, it is helpful to know the solubilities of ionic compounds. Okay? That comes from this chart. You guys need to understand how to use this chart because it will be given to you on a test, and you will need to understand how to predict whether a solid product will form when you put 2 solutions together. So there's lots of water, but is it insoluble in water? The product of that reaction. Okay? So if we look here, compounds containing alkali metals are what? Soluble. Are there any exceptions to the solubility of alkali metals? None. There are no exceptions to the solubilities of alkali metals. 0 exceptions. So if I have an alkali metal and it is packed onto an anion, is it going to dissolve in water? Yes, because it is what? Soluble. It is soluble. Where are the alkali metals on the periodic table? First column. lithium, sodium, potassium, rubidium, cesium. Those are the alkali metals. Okay? It's important to understand that because when we come down here, carbonates are what? Carbonates are insoluble. Unless they are with what? An alkali metal. So, is sodium carbonate soluble or insoluble? Soluble or insoluble? Okay? Carbonates are insoluble unless what? Is sodium an alkali metal? Number 11? Only the first column. First column metals, always soluble. Sodium carbonate. Okay? What about magnesium carbonate? Magnesium is in the second column. Those are the alkali earth metals. They are not alkali metals. It is only the first column that are alkali metals. Therefore, only the first column would make it soluble. So if it's with one of the metals in the second column, it is what? It is insoluble. Okay, we're not looking at if it has a metal or not. We're looking at whether it's a metal in the first column or not. So sodium's in the first column, right? Soluble. Magnesium is in the second column. Insoluble. Okay? So, what is this one? Good. Hard word to say. Okay. Insoluble. So, have you ever heard of milk of magnesia? No? Yes?
The one that when you feel bad, what would you do?
The medicine, isn't it?
Yeah. Milk of magnesia. Why do they call it milk of magnesia? Because it's a white solution.
Like milk.
Because it's insoluble. It's magnesium hydroxide. That's what milk of magnesia is. It's an insoluble product that's not dissolved. That's why it's all cloudy and white. It's a solid. Well, whether it's good or not, don't drink a lot of it. Because
you feel bad on your stomach.
yeah, it can settle your stomach, but if you take too much, it's also a laxative. Yeah. So
So you need to go to
yeah. Like
yeah.
depending on the situation. That's right. Yeah. Yeah. No, bad idea. Okay, so, but that's just a good example of, it's a solution, but it's a solid product. It's not dissolved into the water. It's just a solid product. It's just like the chalky stuff that's just not really dissolved into it. Okay? That's the magnesium hydroxide. Okay, now we're doing this example again for some reason. They like it. Okay, lead nitrate, sodium chloride, lead chloride solid, and sodium nitrate. Let's see from this chart whether that is true. Here's chlorine. Is lead chloride a soluble or insoluble product? It's insoluble, but here it's telling me that chlorines are what? But are there exceptions to the solubility of chlorine?
Yes.
What are they?
lead, silver, and whatever. Mercury.
Good. Lead, silver, and mercury. So lead chloride is an exception to the solubility of chlorine. So chlorines are mostly soluble, but if you put it with the lead's going to find that chlorine, and they're going to get together, and water is not going to be able to pull them apart. Their attraction is too strong. It's a love story. Okay? So, that lead chloride is going to come together. That would make it insoluble, because it's an exception to the solubility. If it's an exception to the insolubility, that makes it what? Soluble. Good. Okay? So, let me try this one. Calcium sulfate, CaSO4. Soluble or insoluble? Calcium sulfate. Okay, so sulfates are what? But there is an exception. Calcium is one of the exceptions to the solubility of sulfate. So calcium sulfate is what? Yes. This chart will be on your reference material. It's there already. Okay? Alright, so that's how we're reading this chart. That's how we're going to read it. Okay? We are going to predict whether it is soluble or insoluble based on where it falls in the chart. Okay? Some of the highlights: alkaline metals are always soluble, ammonia is always soluble, and nitrates are always soluble. There are no exceptions to those. Okay? But most everything else would have some exceptions to it. So if you're trying to dissolve something that is mostly insoluble, like a carbonate, what are you going to put on it? So it will dissolve. You're going to put an alkaline metal on. Or ammonia. Ammonium carbonate would dissolve. Sodium carbonate would dissolve. Potassium carbonate would dissolve. Mostly these things are delivery molecules. Okay? They're always soluble, so they will never form a solid product. They are molecules that help us deliver the thing we want to deliver.
Transporters.
Yeah. What's going to deliver lead? The cation. What's going to deliver lead into the solution? It's not on there. But for the most part, a lot of lead things, see here, lead, they are insoluble. So how am I going to get it into solution? I can't put a chlorine onto lead and deliver it, right? It's not going to come apart. What can I put onto lead to make it so it'll form solution? What? Paint? You say paint? Oh my gosh. Yeah, they don't respond to torture, unfortunately. A halide? If I put a halide on lead, what's going to happen? Insoluble. I can't put a halide. But what can I put onto lead? I could put a carbonate? No. I could put, well, not ammonia because that's a cation and lead's a cation. No, because those are cations. How about one of these guys? Yeah. The nitrate. Remember, that's how we got it, lead nitrate. Or lead bicarbonate. That would work.
Bicarbonate.
Okay. Oh, bicarbonate, yes. Bicarbonate. So those things deliver. They will deliver. These guys are going to deliver the cation, these guys are going to deliver the anion. These are the anions that are insoluble. If I stick one of these guys onto these guys, they will dissolve. Okay? All right, let's look at some examples. I'm going to change one of their examples because this one. So instead of potassium acetate, we're going to do potassium sulfide. Potassium sulfide. K2S. Didn't write very well. K2S. Okay? K2S, and let's do K2S and magnesium chloride. Okay? Those two things. I'm going to dissolve those two things, pour them together. Do they form a solid product or not? Okay? That's what we're trying to identify. Okay, so this is what I would do. I would start by writing the ions, what they are above each of those, to identify what the ions are, and then switch the partners. It's a double replacement reaction. What are the potential products of that reaction? And then go back and determine whether they are soluble or insoluble. So write down these two examples, and I'm going to go back to the other page. Okay, so go ahead and write them down. And then I'm going to go back to the other page, and we will identify whether there are soluble or insoluble products in these reactions. Okay, so kind of forget about this. It's K2S plus MgCl2. Potassium sulfide and magnesium chloride. Okay, I'm going to go back to the other page now. Clear it. Okay, so that's your reference. Use that to decide what are the products, if there are any, of this reaction. A product of the reaction would be a solid. If it is aqueous, if it remains dissolved, then no reaction actually occurs. So the only time you'll actually have a reaction is if there is a solid product. So the products of the first reaction. The first reaction, we have silver chloride plus potassium nitrate. What did you guys find? Is silver chloride soluble or insoluble? The first reaction. Yeah. So these are the products of that reaction. Are they soluble or insoluble? The first one's insoluble. This is a solid.
And the other is soluble.
Potassium. And nitrate. Nitrate is also one of those that is always soluble. So, it's aqueous. That means it's soluble. This silver chloride is a solid. Okay? It is insoluble. Good. Now, the products of the second reaction, we had magnesium sulfide and potassium chloride. sorry, what was that? If it is soluble, it's aqueous. If it's insoluble, it's solid. Okay? So, magnesium sulfide. Is it soluble or insoluble? What do you guys? Good. So it is a solid, right? Potassium chloride. Soluble or insoluble? Soluble. So it's aqueous. Those K and Cl's remain dissolved. Okay? They don't form a solid product. Okay. Good. Okay, now we're going to talk about a few other reactions, types of reactions. Reactions with oxygen, we call those combustion. If you react something with oxygen, you combust it. Okay? So here, we have a combustion reaction with a organic molecule, methane. You react it with oxygen and it forms carbon dioxide and water. Well, anytime you combust an organic molecule with oxygen, it is almost always going to form carbon dioxide and water. Okay? So anytime you have an organic molecule, for example, this one. If I react it with oxygen, it's going to form carbon dioxide and water. Does anybody know what this one is? Glucose. Glucose plus oxygen forms carbon dioxide and water. We call that process cellular respiration. Respiration because it's like respiring, breathing, right? We call it cellular respiration because the cells, in our bodies, they take up glucose, sugar, and they take oxygen from our blood. Those two things go into the cell. They react those two things together, not like maybe what you're thinking, not directly, but very indirectly. They react those two things. And the products of that reaction are carbon dioxide and water. What do we breathe out? We breathe that in, right? We breathe the oxygen in, and we breathe out the carbon dioxide waste. Absolutely. All the sugars that well, if you don't react the sugars, what do? They get converted into fat. So you know those candies that are all like, this is fat-free. Pure sugar, fat-free. Well, if you eat it and you didn't need those extra glucose molecules, those extra sugar molecules, then your body's going to convert them right to fat. Yeah. So, yeah, like all that soda. If you guys realize how much sugar was in a soda.
Yeah, we have
Do they? Okay, yeah. So that's like drinking candies, like tons of candies, right? And all those glucose molecules, it's fat-free. Soda's fat-free, but guess where that's...
Would it give you energy?
Yeah, if you actually needed that much sugar. Maybe. But then again, you can get those sugars from pasta. That's a better way. Those are carbohydrates, sugars. Okay? It'll break that. Your body will break down the pasta into its sugars. Okay, cellular respiration. That's this process. Glucose plus oxygen produces carbon dioxide and water. Well, let's write it the other way. Carbon dioxide plus water produces glucose plus oxygen. Who does that? We don't do that. Plants do that. What? Yeah. We call that photosynthesis. Plants make the sugars that we eat, and they produce the oxygen that we breathe, right? So they make the sugars, they produce the oxygen. Well, fruits, all the fruits are storage for sugar. Every plant makes lots of sugar. Okay? Every plant that photosynthesizes, because the plant uses the sugar itself too, but then it also stores sugars in things like fruit. It has sugar stores, and it produces oxygen for us to breathe. Okay? So, we need plants, right? Plants are important to us. Do plants need us?
Yeah.
No? Because guess what? Plants do this also, all on their own. They do it all. Plants are all fine, all on their own. They don't need us. But we need plants. What's that? Plants don't need us. They do not. Yes, but plants do this. Plants undergo cellular respiration. And they undergo photosynthesis. They do it all. But we don't. We only do a cellular respiration.